Welcome to this explainer. Okay, today we are tackling something literally every single student, researcher, and academic has bumped up against at some point, turning messy, sky-high ambition into focused, achievable academic research. We're going to break down exactly how you take a massive, world-changing idea and distill it down into a project you can actually, finish.
So let's kick things off with a question we've probably all asked ourselves at least once. Have you ever bitten off way more than you can chew when designing a project? Seriously, you start with an idea that's absolutely going to revolutionize an entire field, and before you know it, you're drowning. Just drowning in unmeasured variables, missing equipment, and those terrifying looming deadlines. The hard truth is, most projects don't fail at the end. They fail right at the very beginning, all because of a fundamental mismatch between ambition and real-world resources.
Here is our roadmap for the explainer today. 1. Ambition versus academic reality. 2. A case study on freeze-drying. 3. A case study on therapy balls. And 4. The universal rules for feasible research.
All right, Section 1. Ambition versus academic reality, the academic trap.
Let's look at the classic student trap. It's that massive gap between a brilliant theoretical idea and the grounded reality of lab time, ethics approvals, and, actual academic constraints. The academic support desk notes state, the submitted idea is scientifically relevant, but it is too broad in its present form. Listen, enthusiasm is wonderful. It's the absolute engine of science, but ruthless focus, that is what actually gets a study completed. If your scope is too wide, you will simply never cross that finish line.
Moving right along to Section 2. Case 1. Freeze drying, narrowing the scope.
Let's see how this plays out in the real world. We've got a third-year undergrad named Kaniki Hamaja, and her project completion date is locked in for September 2026. Now, she submitted a project on freeze drying, wanting to optimize freezing rates, map exact collapse temperatures, and enhance reconstitution for long-term storage. Okay, that is dangerously broad. In fact, that's pharmaceutical industry-level ambition. Notice the shift she needs to make here to actually make this doable. Instead of mapping exact collapse temperatures, she needs to narrow it way down to testing the rehydration ratio of, say, a simple freeze-dried carrot cube. We've got to move from impossible ambition to a single measurable product with just one or two distinct variables.
But here's the really cool part. Instead of just a flat-out rejection, the support team gives her this incredible menu of feasible topic directions based on a rapid evidence map. Look at how strict constraints can actually guide you to perfectly clear outcomes. If she wants a food option, she could test the effect of pre-freezing temperatures on fruit slices. If she's got a hot air dryer handy, she could pivot to an alternative option, comparing freeze-drying to hot air drying on fruit pulp. There's a storage option focusing on a short-term 4 to 8 week stability test, and even a biotech option, looking at lactic acid bacteria. Well, assuming she has access to the microbiology facilities, of course. The vital takeaway for your own work here, match your research question directly to the equipment you actually have sitting in your lab right now.
Now, equally important is knowing exactly what not to do. The guidance notes explicitly list what a third-year undergrad should avoid. Look, unless you happen to have a fully funded pharmaceutical manufacturing facility hidden away in your dorm room, you should absolutely avoid OCT-based collapse temperature mapping, highly concentrated monoclonal antibody formulations, multi-omics, or industrial-scale energy optimization. Trying to juggle advanced variables like chamber pressure and packaging all at the exact same time is basically a guaranteed recipe for a stalled project.
Okay, Section 3, Case 2, Therapy balls, a different discipline.
Let's see how this exact same core problem pops up in a totally different field. Our second student is Geethika, a postgraduate physiotherapy student. She's studying the effect of structured therapy ball activities on balance in children with autism spectrum disorder. But there is a massive red flag in her file. She has already started data collection without finalizing her protocol. Yikes. So, the crucial point here is honesty and scientific framing. Is her project a randomized controlled trial, or is it a single-group pilot study? Because the direct evidence base for therapy balls as a main balance intervention in autism is extremely limited and preliminary, this has to be framed honestly. If there is no control group, it's a single-group pre-post pilot or feasibility study. It is definitely not a definitive efficacy study.
To figure out her outcomes, Geethika is using the Pediatric Balance Scale, or PBS. Honestly, instead of juggling a dozen complex metrics, relying on a focus tool like the PBS is incredibly smart. It captures functional static and dynamic balance tasks to produce one clear total score. The academic support desk notes this is a highly acceptable, practical metric for a postgraduate project, provided, of course, the child can follow simple instructions and remain completely safe during the testing.
She's also using the timed up and go test, which we usually just call TUG. Think about how wonderfully elegant this is in its simplicity. It captures functional mobility and dynamic movement performance, and the whole thing is measured entirely in seconds. A lower time simply indicates better functional mobility for the child. Using these kinds of established, straightforward metrics is exactly how you keep a study feasible while still producing highly valid, really meaningful results for your patients.
But, because Githika jumped the gun on the data collection, the support desk had to hand down a pretty stern do not do this list. First off, do not claim therapy balls are already proven to improve balance in ASD. The evidence is just way too low level right now for that. Second, do not call the study an RCT unless true random allocation is actually happening. Third, do not ignore concurrent therapies. This is a huge one. If the child is also getting occupational therapy or sensory integration therapy at school, that undeniably influences your outcomes. And finally, in your statistics, please do not report only p-values. You have to report pre- and post-means, standard deviations, and effect sizes. Faking an RCT design or jumping to unproven conclusions, absolute cardinal sins in clinical research.
Which brings us to Section 4, Rules for Feasible Research, Universal Guidelines.
Seeing how these totally different disciplines face the exact same hurdles, let's pull it all together and synthesize the universal rules. Here are the actionable steps every researcher has to take. Step 1. Confirm your facilities and ethics. For Githika, because she's already out there collecting data, confirming ethics approval within 48 hours is mandatory. Like, data collection cannot continue without it. Step 2. Select one primary research question and one primary outcome. Step 3. Choose 2 to 3 peer-reviewed papers that perfectly match your method and read the full texts. And Step 4. Prepare a one-page concept note before you touch a single piece of lab equipment or recruit even one patient.
Using a standardized one-page concept note template literally forces you to stop juggling a million variables. You have to write down one clear title. You must list your exact material or sample, like carrot cubes or children aged 6 to 12 with documented ASD. You define your single independent variable, your primary outcome, and the exact basic statistics you're going to use, like a paired t-test. This standardized format is practically a roadmap to sanity. It clarifies exactly what you are doing from day one and makes sure your proposed project actually matches the physical resources you have available to you.
And that brings us to a pretty strict boundary regarding academic integrity. The support documents clearly state guidance is limited to topic refinement, methodology QC, final writing must be done by the student. Academic support desks, advisors, mentors, they're all there to provide intellectual guidance, statistical direction, and evidence-based feedback. But they will never, ever write the proposal, the thesis, or the manuscript for you. The ownership of the work, and honestly, the profound learning that comes from doing the actual writing, always remains with the student.
I want to leave you with this provocative thought as we wrap up this explainer. What if embracing your academic constraints actually became the catalyst for your greatest scientific innovations? Seriously, what if the limits placed on your equipment, your time, and your scope aren't obstacles at all? What if they are the exact focus you need to stop dreaming broadly and start discovering deeply? The next time you face a constraint in your research, don't fight it. Use it. Use it to carve out a clear, measurable, and impactful study. Thanks so much for joining me, and I really hope this helps you design your next great project.